Okay, good evening. Let's get started. Today we're going to talk about OpenCL device architectures. Today's class will cover these several topics. We will introduce processor architectures and the innovations that people have been employed in improving the processor's performance. And we'll talk about architectural design space, and we'll describe in more detail CPU architecture and GPU architecture. And later half of this class, we will look at FPGAs, as it's an emerging and interesting high-performance architecture that we can program using heterogeneous computing programming languages and frameworks. So last week, we primarily talked about the general concepts of parallel computing, heterogeneous computing. We didn't talk too much about OpenCL. Starting from today, we're going to introduce you some of the basic concept of OpenCL. Although, as you expect, we will spend more time in later weeks to talk about the details. But throughout today's discussion, we will try to make a connection between the processor architecture with the OpenCL framework. OpenCL is a collaboration among many companies starting from a decade ago, and it has been shaped by many vendors for many platforms. It started from the GPU processors in the early days, where the GPUs have some shading accelerators on chip, and people started to thinking about how to use these hardware accelerators for general purpose computing. And to extend in that direction, people have been trying to have this unified, universal programming framework that can target to different processors from different vendors. But the reality is the processors provided by different vendors, they have different goals, and their target market, their features are quite different from vendor to another vendor. So while people are designing OpenCL, the OpenCL framework has been gradually shaped by these vendors based on the processors they provide. Of course, OpenCL has the capability of detect hardware capabilities. So it will know through well-defined APIs what kind of features a processor can provide. And because OpenCL has to deal with a variety of different processor architectures, it has a relaxed consistency block-based parallelism model, which runs on different processor architectures, symmetric multiprocessors, multi-threaded microprocessors, or single instruction multiple data, or vector processors. And basically, it assumes very little from the underlying processor. It tries to achieve platform interdependency. The performance of OpenCL programs still depends on the implementation, the algorithm, and also how well it can be mapped to the hardware architecture it utilizes. We'll see more as we understand in depth these different processor architectures. Overall, when people design different processors, they have many things to consider, and oftentimes they have to make design trade-offs. For example, you have to think about, okay, do you want to have a single core processor or multiple processor? If there's a single core, what kind of internal designs you want to leverage to improve the performance? And the definition of the course varies. There are different kinds of cores. Superscalar core, which is kind of when people start looking at how to improve a single processor performance, they look into at instruction level how to schedule the instructions earlier, how to execute them at the same time with other instructions. Also, SIMD or VRIW are all the examples of the design options. Also, when we talk about cores, we also are interested in integer and floating point performance, and also multi-core versus many-core. So if you want to use the transistors on a single chip, do you want to have a few large cores, or you want to have simpler but many of those? The reality is it might be challenging to keep cores busy because you don't know what we're going to run on these processors. Also, the design consideration involves multi-threading. Multi-threading is one way to increase the amount of useful work available to occupied compute resources. Because chances are, if you have a program, it will have to read data from memory before it can compute. But reading data from memory takes time. While you're reading data, if you are not having multiple things to have the core to compute, then the core is going to stay idle. So multi-threading is a way to increase the amount of useful work the cores can work on. Also, cache and memory hierarchy are important design options. How many levels of cache, and what are the sizes of each level of caches. Heterogeneity is becoming more popular in modern processors. You likely see these heterogeneous processors on the single chip, or I should say heterogeneous cores on a single chip. CPU plus GPU, CPU with FPGA, and also big and small cores. And also performance scaling limitations. While you are shrinking the transistor size, there's a limit. You can lower the supply voltage or increase the frequency. Conventionally, CPU is optimized to minimize the latency of a single thread. A single thread can be, a stream of instructions from one program, and we would like to efficiently handle control flow intensive workloads. In other words, we want to be able to execute any programs, even though they may have a lot of branch instructions. And that's why we have to use a lot of transistors or a lot of chip area for caching and for control logic. Caching, as we see later, that is a nice way to exploit the temporal and spatial locality while you're executing a program. And this control logic is an important part of the design because you have to deal with these complex control flows, and also you want to use novel designs, smart designs to be able to execute more instructions at the same time using all the on-chip resources. Traditionally, there are limited number of registers because of the smaller number of active threads. So if you have only one thread that you assume you will execute, then there's no need to have large number of registers. I said earlier that control logic is important. These control logics are used to reorder the instructions to exploit instruction level parallelism that inherent in the programs.